So far, we saw our singular value decomposition on this small users to movies example, where what we saw was basically we took this original matrix and we were able to represent it as a product of 3 matrices. And there we talked about the sci-fi concept, the romance concept, and then there was this also the third column that we kind of had very low strength, right? The third concept that had very small strength that we kind of brushed under the rug and didn't really talk about. So what I want to do now is actually talk about how do we do the dimensionality reduction. In a sense, how do we discover that our movie data really had only 2 real kind of strong concept, and the last third concept was more like noise, and it was okay to kind of remove it from our analysis and discussion. So the idea is, what is SVD really doing, and how do we think about it in terms of dimensionality reduction? And what SVD is really trying to do, it basically, in some sense, it gives us the best axis to project on. So what do we mean by this is that the best means that the sum of the squared projection errors is minimized. Okay, so in some sense, we want a small set of axes such that if we represent our data in terms of that axis, we get the minimum reconstruction error. And the simple example how to see this would be in this 2-dimensional example, where imagine every different axis is a separate movie, and we have users ranking movies, and every point is now a user, and the x position of this point is how much they rated movie 1, and the y position is how much they rated movie 2. And assume that our data lies in this kind of shape. So then if we think of it and say, okay, we are only given 1 coordinate to be able to represent this data. So not 2 coordinates, but I only give you 1 coordinate. What is the best axis along which you want to represent this data? So for example, in this case, this would be the best axis. And now every data point we can represent as a single number, which is simply the position or the projection of a given data point on this line. So for example, the data point that I'm just drawing, the red data point here, would project to this line, to this particular location. And now my goal is that when I now represent these 2-dimensional points simply by their position along my red line, the sum of the squared errors of their locations, so basically the distance between its true position and the position among the line should be minimal. And this is exactly what SVD does. So what SVD does is finds the best vectors or axes on which to project the data such that the reconstruction error is minimized. So let me give you an example of what do I mean by this. And now, for example, also the question is, given this 2-dimensional data, how do I discover the best axis on which to project? And how do I really do dimensionality reduction? How do I discover the position of the point on this given line? So the idea is the following. We are given our matrix A, and we represent it as a product of 3 matrices, U sigma and V transpose, where we think of V as a movie to concept matrix and U as a user to concept matrix. So what this means immediately that we see that V is a movie to concept matrix, which means that, for example, if you want to ask what is this vector V1 along which it is the best to represent the data, that is simply the first row of our matrix V transposed, right? So this is exactly the vector that represents the axis of the highest variation. So I have still our old example of users to movies represented in the SVD of this thing. And now the question is, how do we do dimensionality reduction? So for example, the way we do dimensionality reduction is that we can think of the whole system the following, that our first right singular vector gives us the location, the axis on which we want to project, and then the corresponding singular value tells us the variance along that given dimension, or the spread of the values along that given dimension. So in our 2-dimensional case here, the values are really spread around the first singular vector, they are spread around a bit the second singular vector a bit less, and they are not really spread around the third singular vector. So the strength or the importance of that vector is very small. So now what we can think of the locations the following. So far I talked to you what defines the axis. Now the next question is what defines the positions or coordinates of the points in this new space. And the way we can think of that is that we simply take the matrix U and multiply it with sigma, right? And this gives us the coordinates of the points on this projection axis, right? So basically, how do they map down to our lines, right? So for example, if I compute, given my matrix A, I compute the product of U times sigma. Here is now the position of every user in this new space, where, for example, the first vector simply tells us what is the location of every user along the first right singular vector. And for example, here you see that the values vary quite a lot along the first one. They vary quite a lot along the second one, right? The range is very high. But for example, the third one, everything is kind of around 0, or the variation along the third column is much smaller, which is why the third concept had a very small weight. So now, given that we have our matrix A, and again the singular value decomposition of it, the question is, how do we really do dimensionality reduction, right? So far I just showed you how we can represent the original data points in this new projected space, but the question is, how do we really do dimensionality reduction? And that turns out to be very simple. All basically we need to do is we need to go and set a given set of singular values to 0. And basically we take the smallest, if we want to preserve k dimensions, then basically we take r minus k smallest singular values and set them to 0. So for example, in our case here, if we want to do dimensionality reduction from this 3-dimensional space to a 2-dimensional space, all we need to do is take this the small singular value, set it to 0, which in some sense means that now we also take the third column of U and the third row of V transpose and set them to 0. So the way we can do dimensionality reduction is to now take U, the new sigma, and the new V transpose, where we took the last singular value, the last singular vector, and the last right singular vector. We set all of those to 0. So if we would now, for example, go and take the three new matrices that are now smaller, right? They only have 2 columns and 2 rows, and multiply this thing together. Here's the matrix we would obtain, right? So here's our original matrix A. Here's our new matrix A. Call it A prime, or let's give it a name B. And what you notice is that A and B are very similar to each other. So what do I mean by similar to each other is that if I take a given element, for example, this number 5 here, and I compare it to this value here, to the same axis to the same cell in matrix B, we see that the difference is very small, right? Or for example, I can take this 0 here, compare it to the corresponding element in B, and again, I see the difference is very small, right? So what we basically did is we took, in the previous slide, we took our original matrix A, represented it, did SVD, and we were able now to exactly reconstruct it. Now we actually took, removed a few last column from U and the last column from V, and we removed the singular value. Now we represented everything as a smaller set of matrices, so these matrices are now smaller. If we multiply the 3 matrices together now, the new matrix we obtained was very similar to the original matrix A. And when I say very similar, we can quantify the similarity of 2 matrices using what is called the Frobenius norm, right? And the Frobenius norm of 2 matrices is simply the sum of the differences of their entries, right? So if I say I have matrix A, I have matrix B, so their distance, their Frobenius norm is simply I take a summation over all the entries, I take the difference of the entry values, sum them up, square that up, sum those entries together, and take a square root, and that's my distance.